Hi, so this video gonna show you on one of the sample midterm question on force vibration. So if you look at these questions, you have a bar problem or a rigid lever basically, and you do have a force Ft. Okay, so normally when we have this kind of questions, make sure you list out and perhaps highlights on the values given. So put it in terms of variables, okay, when you read the question. So if you take a look at this, they gave you the J naught. So I already list down what are the variables given. The J naught is given. They define Ft as F naught cosine omega t, and they also give you the equation of motion. So it's kind of fairly easy. It's just then you have to list out in terms of what are the things that you need to find. So in A, you can see here I also listed out all the things or summarize the questions. A, you have to find the free body diagram, as well as you need to express the undamped natural frequency. Okay, I listed it as omega n. And part B, you want to find the steady state angular oscillation, okay, which is capital theta here. The steady state angular oscillation is given, okay, and you want to find basically your C, damping constant, as well as zeta. So I've highlighted here. These are the things that you want to find, and I listed all the values given related to this question. And part C, so you can see it's fairly easy. Once you know what are the variables given, then you can easily relate to which equation you're going to use. Part C, you can see if the damper is removed. So there are conditions here. So you may want to read this question very thoroughly, maybe 2 or 3 times so that you understand what it wants. It says when the damper removes, so you know damper normally relates to C or zeta. So when it is 0, okay, what would be the amplitude of the steady state? So amplitude of the steady state angular oscillation. So angular oscillation is theta. The amplitude is capital theta. If it says amplitude of the steady state, means your steady state response as well relate to damping. Okay, so basically this one, the second part of it is on the effect of C on theta steady state. That's why it says here, briefly explain the significance of damping on the steady state response of the system. Okay, let us go ahead and solve for part A. Part A is they want you to draw the free body diagram. So I have put here the basic lever, the illustrations of the lever. What is it? How is it going to look? Basically, I always tell the student we want the Ft in your EOM to be positive. So that's why, if you remember, the first step of drawing your free body diagram is basically you have to assume the direction of motion. So in this case, we assume counterclockwise because you can see that your force is going upwards. Yeah, so you can imagine that this bar is going to go upwards as well. Okay, so the bar will go like that. So that's why we are choosing counterclockwise, so that in your EOM you get positive. But that doesn't matter because in this question we already give you the EOM. The main thing is once you decide, so after you decide the assumed direction, in this case counterclockwise, then you draw the lever as shown here. Okay, I've drawn the lever. Then you can actually draw what happens to the spring and the damper. So in this case, the left hand side of the bar, so remember this is the pivot point O, the left hand side of the bar will go down, so your damper will go down, as well as your spring will also go down. Okay, then only I've put also Ft there. Yeah, so then only you draw action reaction. So the action reaction should exactly the same and opposite. So that will go up as well as that one will also goes up. So that's all for the free body diagram. Okay. So basically, they want you to get the omega n in part A. So in this question, they already give you the equation of motion. So it's fairly easy. You do not have to get your equation of motion or derive your own equation of motion. Okay, before that, let me just write the force here. So this one, to complete your free body diagram, I forgot to write the forces. Okay, so basically this is a linear damper. Okay, to write the forces, so this is basically x. Okay, L1 theta is basically x. It's a linear damper. It should be x dot. Yeah. So in terms of L1 theta, in terms of theta, so x is equals to basically L1 theta because it's a rotation. Okay, same as for k. It's supposed to be a linear, so it should be kx, but your x for the k is basically L1 k L1 theta. So that's what it means. Your x is equals to L1 theta because you convert it from linear to kind of like a small triangle, if you remember. So this is x, this is L1. So this is like a radius of this small triangle. So that's why your x is equals to L1 theta. Okay. Okay, so I've just put a note on the derivation of how you get L1 theta dot and L1 theta. So if you rearrange the terms, that's how you get the equation of motion here. So now we want to get the omega n. Okay, so omega n, if you remember the equation for, if it's rotational, if it's translational, it's just square root of k over m, isn't it? But if it's rotational, is square root of k over j. Okay, so, but everything should be not this actual k that we have in this question. It's actually k equivalent and j equivalent. So in this case, your j equivalent is also your j naught. Alright, so you have this expression as your j naught, and also you have this coefficient for your theta is basically your k equivalent. Okay, so this is your k equivalent, and this is actually your j naught. It's just the same. So to answer the second question, so basically your omega n is equals to, your k equivalent is KL2 square divided by j naught. Alright, so that will be the answer for this A, part A. Okay. Part B, you have to find C and zeta given all the values for your capital theta. So if you look at your list of equations, so I already included here. So from your list of equation, you can see under harmonically excited vibration, this a linear system. As I said, you need to convert it into the torsional system. So your capital X becomes capital theta is equals to, so F naught is basically your moment. Okay, where do you get your moment? So basically you can also look at here. Your moment is all the expressions over here. Yeah, F naught L2. So basically your F naught L2 is the coefficient, whatever coefficient on the left hand right hand side of your EOM. Then you have your K. So all these values, the K, the M, the C should be equivalent values. Yeah, it's not actual K or C value, it's the equivalent values. So if you want to write, it's basically your K equivalent. Okay, so if you actually match from the list of equation, you can see your F naught becomes the moment. Okay, as I said just now, F naught L2, then your K become K equivalent, your M becomes J naught in this case. Your C is actually your C equivalent, and your omega is still the same. So from that equation, you because they want to get you to have to find what is your C. Okay, so we have to rearrange this equation in terms of C equivalent. So after you rearrange, so I have rearranged this for you, then you substitute all the values, you can get C equivalent as 772.8. So you know, if once you get your C equivalent, you can actually calculate your C, because if you look at the equation of motion here, your C equivalent is basically here. Yeah, your C equivalent is CL1 square. So CL1 square is your C equivalent. CL1 square. So from there you can calculate your C. Okay, not C1, yeah. You can calculate your C is equals to your C equivalent divided by L1 square. So if you substitute that, because all the values are already there, so you get this. So you can finally get your C. Once you get your C, you can calculate your zeta, because zeta is C equivalent divided by, it's actually, look at your list of equation, is C divided by 2 square root of km. So your K is actually K equivalent. So all the terms in your list of equation is actually in terms of equivalent values. Yeah. So if you substitute that, you can check this, you get this. So we've done with part B. So for part C, when your C is equal to 0, so if you remember, we have this equation in part B, but now what they're saying is this part here, so your C is equals to 0. So when this is equal to 0, then will be easier, because now basically your, so if your C equivalent is equal to 0, then you will just end up with this equation. So it's easier because you do not have the square root term anymore. Yeah, you only have one term at the denominator. So from there, you can actually get and calculate your capital theta. So you get your capital theta as 0.038 radian. So that is when your C equals 0. And they want you to check on the omega n as well. So that we can see whether it's actually near resonance or not. You can recalculate your omega n, which is now your value is, if you actually calculate your omega n with the values of substitution, basically you get 41,000, the K equivalent over J naught just now, because just now we just give it in terms of expression, but if you calculate, it's actually 77.09 radian per second. And your omega, I think you have you need to actually change just now your omega 750 rpm, you have to times 2 pi over 60. So basically your omega is 78.54 radian per second just now. So looking at this value, the 78.54. So you can see that under this condition, your omega and omega n are quite near. So you would expect that when you have damping, okay, so when you have damping or maybe higher damping, okay, it actually results in reducing your steady state response. Okay, or you can also compare use part B and part C. So in part B, you know that your omega or the amplitude is 9.88 radian, but now without damping, okay, it actually increase a lot. So when you actually add damping, okay, then you can actually reduce your amplitude as well as reduce your steady state response. Okay, so I think that's all. That should make sense when you have higher damping, it will actually reduce the peak. Okay, I think that's all for all the solutions for part A. Okay, we have done part A, part B, and also the final answer for part C. That's all. Thank you very much.